So hello everyone, I am Somnath Hazra. I hope you can see my screen. So this is a live interaction session on CS100 operating system fundamentals, and this week we will be discussing some problems related to threads and scheduling. So this is the 5th week of the course. So without further ado, let's get to the questions. So this is the first question. So it is related to Amdahl's law. The question goes like this. So let a program have 40% of the code enhanced to run 2.4 times faster. So what is the overall system speed up? So this question is related to Amdahl's law. It's a very simple question. You can directly apply the formula if you know. Yeah, can you tell me the overall system speed up? So 40% fraction of the code is enhanced to run at 2.4 times faster. So what will it, how much overall speed up will it result in? Would anyone like to contribute? You need to calculate the overall system speed up. It is given that 40% of the code, that is 0.4 of the code, runs at 2.4 times faster of how much fast it was running previously. So you need to calculate the overall speed up using Amdahl's law. I'll wait for another minute. Anyway, so as you may know, this session is being recorded. So yeah, just a heads up. Nothing like that. Nothing else important thing. Anyway, let's get to the answer then. Okay. So the fractional speed up is 2.5 times, as I said, and the fraction that is enhanced is 0.4 of the fraction of the complete code. So the overall speed up, as you may know from Amdahl's law, is that 1 by 1 minus f. F is the fraction that is enhanced, plus f by the times that it is enhanced. So this is the complete formula. So if you put the values accordingly, you will get these. You will get the value, that is the overall speed up is 1.32. So if the older code was running at 1x, the newer code will run at 1.32x. So this is the formula for Amdahl's law, if you did not know it previously. So in this case, we have eliminated the time variable. So we have taken that the older execution time to be 1, and then we are calculating the newer execution time. So we have eliminated the time variable, so there is no question of seconds or something like that, because it will get crossed out above and below. So the fraction, so how to calculate the newer execution time is older execution time multiplied by this complete equation that you see, that is 1 minus the fraction that is enhanced, plus this represents the fraction that is not enhanced, that is not speed up, that does not speed up. Okay, so plus fraction enhanced divided by the speed up that we have used. So in the older problem, so 0.4 is the fraction that is enhanced, so 0.6 is the fraction that is not enhanced. So if you do 0.4 divided by 2.5, you will get 0.16. So you need to take the reverse of this complete thing. So that by that you will get 1.32. Okay. Anyway, let's move on to the next question. So in the previous session also we were discussing some questions regarding threads. So in this session also there will be questions regarding threads, and we will be discussing some questions related to scheduling algorithms. Okay, so this is a question related to threads. So which among the following is true regarding threads? Can you tell me? That is, do they need to initiate separate variables for inter-thread communication? The fork system call creates copies of all the threads when allowed. The vfork system call creates copy of the current thread only, or there is no separate and there is no separate exec call for threads. That is, the exec system call that stays the same, that was used for terminating processes. So there is no separate special function for executing sorry, not termination of processes. So the exec system call that was there for processes, that stays the same for threads also. So which among the following is true regarding threads? Can you tell me? There can be multiple correct statements also. Would anybody like to contribute to this? So in this session there will be many numericals that will be solved. Just guessing from the topic only, that you can guess that there will be multiple numericals that will be solved. But obviously there will be some theoretical questions. Okay, I got one answer, B. There can be multiple correct answers also. Just one option may not be correct. There can be multiple correct options. Anyone else would like to contribute? Okay, anyway, let's go to the answer then. So just the first statement is incorrect, that is, there is no need to initiate separate variables for inter-thread communication. As you may know, when we create separate threads, the code section, data section, they are all shared, right? So there's already a shared data section in between in between the threads. So we can always utilize that for inter-thread communication, right? So no need to create initiate separate variables. That was used for inter-process communication. If you remember, we when we studied questions related to inter-process communication, we needed to create separate variables for when we created new processes. So using fork system call, we needed to create separate variables also. So for inter-process communication, the fork system call, yes, it creates copies of the threads, copies of all the threads. So in some systems it allows that it can create, when you call a fork from a particular process, so a process may have multiple threads, right? So for all the threads, if it is allowed, there may be copies of all the threads in the new process that is created using fork system call. In order to avoid that, in those systems there is a special system called vfork, and obviously the exec system call exists for threads, that stays the same. Anyway, let's go to the next question. So can you tell me, processes can be single threaded only, multi-threaded only, both single and multi-threaded, or none of the above? Can a process consist of only single threads? Can a process like all the processes, can they consist of only multi-threads? Yes. So this is a very simple question. So yeah, both single and multi-threaded processes can be there. Let's go to the fourth question now. So in a program, 40% of the code is enhanced to achieve an overall system speed up. So what is the maximum possible overall speed up of the code that the code can achieve? Can you tell me? So this question again, as you may know, it is related to Amdahl's law. So it is said that the 40% of the code is enhanced to achieve an overall system speed up. So what is the maximum possible speed up that we can achieve with that? Would anybody like to contribute? So this is also related to Amdahl's law. So just the one factor is given, that is the fraction which is enhanced. So this the actual speed up is not said. So the overall maximum possible overall actual speed up, that is that you need to calculate. So how do you do that? Would anybody like to contribute? Okay, let's go to the answer then. So yeah, so at first we assume that we can in the 40% of the code that was enhanced, we can achieve infinite amount of speed up, right? So the denominator fraction that is here in the formula, so that will be infinity then, right? So if the denominator is infinity, so this term goes to 0 then, right? And in the rest of the 60% there is no speed up, so it will be 1 by 0.6, so that comes to 1.67. so that is the maximum speed up that you can achieve with 40% of the code enhanced. However, you may know that this is a very accurate figure. So although this is the maximum possible, it is never achievable, since you cannot this factor cannot be infinity. You cannot speed up any fraction of the code infinite times, right? So yeah, this is the maximum possible figure, but it is not practically achievable. This is just theoretical. Okay, anyway, so this question again is related to Amdahl's law. Let's go to the next question then, question 5. So if a program is 100% serial with infinite number of cores, so what will be the speed up? So the code is 100% serial and there are infinite number of cores. So anybody would like to contribute? This question is again related to Amdahl's law. So there are infinite number of cores, which is again practically impossible, but for the sake of question, let's think that it is possible. And the code is 100% serial. There is no parallel execution possible. So what will be the speed up then? Anyone would like to contribute? Okay, so if a code is 100% serial, can it take the advantage of multiple number of cores? It cannot execute parallelly. So even if there are multiple number of cores, it cannot take the advantage of that, right? So even if the speed up can be infinity, but since there is no part of the code that can be speed up with that, so everything will be executed serially. So in that case, what will be the speed up? Okay, so this is the answer. So since nothing can be executed parallelly, so everything will be executed serially only, right? So there will be no overall speed up in spite of the fact that there are infinite number of cores that are available which can execute the things parallelly. Okay, so the speed up will be 1, it will not be 0. Okay, if, the speed up is like a fraction of the earlier execution time, so it cannot be 0, it will be 1. So there will be no speed up, but the thing is that in numerical terms we say that the speed up is 1. Okay, so let's move on to the next question then. So a portion, again this is related to Amdahl's law again, as you can guess from the question. So a portion of the code is enhanced to 4 times faster and yields an overall system speed up of 3.3. So what is the fraction of the code that is enhanced? So here you need to calculate the fraction of the code that is enhanced, right? So the code is enhanced, see the overall system speed up that is achieved is 4 times. Okay, the overall system speed up that is achieved is 3.3, right? And a portion of the code is enhanced to run at 4 times faster of what it was running previously. So the fractional speed up is 4, the overall speed up is 3.3. So what is the fraction of the code that is enhanced? So it is you have to assume that a single fraction of code is only enhanced to run to 4 times faster. To run at 4 times faster of what it was running previously. So anyone would like to contribute? So you have to make use of the Amdahl's law again. So the overall speed up equals to 1 by 1 minus the fraction that is missing plus the fraction that is missing divided by 4. So that is the formula that you have to use. Now you have to find out the fraction that is missing. What fraction of the code is speed up by 4 times so that we can get an overall speed up of 3.3. By the way, can anyone tell me that can we achieve an overall speed up of more than 4? So that is not achievable, right? So a fraction of the code is running at 4 times faster, but at maximum what fraction of the code can it be? That is 1, the complete fraction. Just a second, just give me a second. So if anybody has any answer, so as I was saying, yes, so the maximum fraction of the code that can be enhanced is the full complete code, right? That is 1. So if you replace 1 in that formula, so you will get 4. at maximum. So that is the maximum possible speed up. It is not possible to go beyond that. That is logical, right? So anyway, let's get back to the question, and anyone would like to contribute to the answer. Okay, anyway, let's get to the answer then. So the fractional speed up that is given is 4 and the overall speed up that is given is 3.3. So let's assume that the fraction that was speed up was f. Okay, so if you replace f in the Amdahl's law, so you will get 1 minus f plus f by 4 equals to 3.3. So now you need to just solve this equation and you will get the value of f, that is 0.929. It is very close to 1, as you may have already guessed, since that fraction is speed up by 4 times and that causes the overall system to speed up by 3.3 times. So it should be a large portion of the system, right, that is speed up. Yeah. Anyway, let's get to the next question then. So multi-threading on a multi-CPU system, can it increase concurrency? Can it decrease concurrency? It doesn't affect concurrency, or it can increase or decrease concurrency? Like it can happen, anything can happen. So which among the following options are correct? Multi-threading on a multi-CPU system, how will it affect? Anyone would like to answer? Someone says it increases concurrency. Okay, I'm getting answers. It increases concurrency. Anyone else? Anyone else would like to contribute? Anyway, so let's get to the answer then. Yes, it increases concurrency. See, on a multi-CPU system, so there can be multiple processors, right? So when there are multiple processors, multiple tasks can be executed at the same time, right? So what that increases parallelism. But what does concurrency mean? Concurrency means that whether the tasks are progressing or not. So even if you have single processor, so that can also support concurrency, right? Yeah, that can also increase concurrency even if you have a single processor. So multiple tasks can progress. Okay, so given that there are multiple CPUs, there are multiple processors, so with that fact, it can only increase concurrency even more compared to a single processor. It cannot decrease concurrency, because the other suppose the processor 1 is executing task 1 and task 2. Processor 2 will be idle, so it can execute another task, right? So for example, task 3. So this is a similar figure to one we saw in the previous session, as you if you would have joined in the previous Tuesday session. So yeah, there also we were discussing about parallelism and concurrency. So yeah, so if you have multiple processors, it can only increase concurrency compared to a single processor. So yeah, so yes, increases concurrency is the correct option. Okay, so let's move on to the next question. So which among the following are shared across multiple threads in a multi-threaded process? Register values, global variables, heap memory, or local variables? So which among the following do you think is or are correct? Anyone would like to contribute? Okay, are shared across multiple threads. Anyone else would like to contribute? So when multiple threads are created, so what happens is the registers and the stack sections, multiple copies of that are created, but the code, data and the heap section that are shared across all the threads of a process, like when you create multiple threads of a single process. So yes, so what happens is the registers and the stack sections are independent. What is stored in the registers and the stack sections is things like the program counter, the temporary variables, the local variables. Those all are stored in the registers and the stack sections, right? So those need to be independent for the independent threads, because they are the primary operations that are happening in a process. They cannot be shared across multiple processes, okay? And they do not take much time to create. So multiple copies they do not take much time to create. So what happens in those cases? So now can you answer? Which among the following are created, are shared across multiple threads in a multi-threaded process? Anyway, let's get to the answer. If anyone is speaking, you'd rather use the chat box, because I may be unable to hear. If anyone has any doubt, rather use the chat box. Okay. Anyway, let's get to the answer for this question. So when multiple threads are created, basically there is a sharing of global variables that is stored in the data section and the heap memory. So the code, data and the heap that are shared across multiple threads, but the threads create their individual copies of the registers and the stack, right? So the local variables are stored in the stack, and the register values of course are stored in the registers. So the registers, one of the registers, as you may know, is the program counter that keeps a track of which part of the code is executing, right? So yeah, that requires a separate copies for the separate threads, since they are separate, right? Anyway, let's get to the next question. This is with regards to lightweight processes. So can you tell me which among the following are correct? That is, the intermediate data structures between the user and kernel threads are lightweight processes. Each lightweight process is attached to a kernel thread. Lightweight processes maintains the number of user threads allocated to the application, or the kernel threads are scheduled by the OS operating system to run in the processor. So which among the following, there can be multiple correct also. So which among the following do you think is or are correct? Anyone would like to contribute? There can be multiple correct also. B and D. Okay. Okay. Anyone else? Okay. B. Okay. Anyone else would like to contribute? So what are actually lightweight processes? So when you create a user thread, it cannot execute on its own. It requires some kernel thread to be attached to it, which is actually given the processor time, which actually gets the processor time for the OS to run, right? So this communication happens through lightweight processors, which are actually data structures between the user and kernel threads, right? So lightweight processes, so as you may know, you can create any number of user threads, but there generally is an upper limit to the number of kernel threads that you can create. So who actually keeps a track of how many kernel threads are created by a particular user process? So that is also done by the lightweight processes, since they are in direct connection between the user threads and the kernel threads. So they actually keep a track of which user thread is creating how many kernel threads. In that way, if any user code is wrongly written and it is going on creating multiple threads in an infinite loop, so that can be checked by the lightweight processes, and that code can be immediately stopped, that user thread can be immediately stopped, so that it stops creating the kernel threads. And as I said, the kernel threads are actually scheduled by the OS to run in the processor. So that are the threads that actually get the CPU time. So yes, so the lightweight processes, as I said, they do not need to maintain the number of user threads. So user threads can be any high number. It does not matter until and unless the number of kernel threads are kept in check. Okay. So that is the only incorrect option. And yes, they are the intermediate data structures between the user and kernel threads, and they are attached to a kernel thread. Okay. So for every kernel thread there is a lightweight process that is attached. Okay. So if the degree of multiprogramming is low, so can you tell me which of the following are correct? There can be one correct, there can be multiple correct also. So these are related to the CPU scheduling criteria times that you have studied. So that is the turnaround time, waiting time, things like that. So CPU utilization is also a CPU scheduling criteria. So now we have moved on to questions related to scheduling. Okay. So which of the following are correct? So the turnaround time and the CPU utilization will be low, the waiting time will be high, the turnaround time will be high, or none of the above. So which among the following do you think is correct for if the degree of multiprogramming is low? Okay, I got one answer. Anyone else? Anyone else would like to contribute? The degree of multiprogramming relates to how many programs or how many processes are there in the ready queue. So we had studied about the states of a process and the queues that are related, right? So the job queue and the ready queue. So the ready queue, the processes are scheduled by the short-term scheduler from the ready queue, and the processes are scheduled by the long-term scheduler from the job queue, if you remember. So anyway, so the degree of multiprogramming refers to how many processes are present in the ready queue. So if that is low, what happens? With respect to a single process, will the turnaround time be low and the CPU utilization overall be low? The waiting time will be high, the turnaround time will be high. So none of the above. Which of the following are correct? Anyone else would like to contribute? Anyway, let's get to the answer. So yes, you are correct. The first option is correct. That is, the turnaround time and the CPU utilization both will be low. Why is that? Because think of an example where you have only one process in the ready queue, and compare that to an example, to a situation where you have two processes in the ready queue. So if you have just one process in the ready queue, that will immediately get the CPU, that will execute in the CPU, and that if it does not have to wait for any IO or something like that, so it will directly be terminated, right? So that is the fastest turnaround time that is possible for a process. Okay, so compare that with two processes that are present in the ready queue. So the short term scheduler will sometimes pick up the first process and give it some time for the for execution in the CPU, and then it may preempt it, or it may go into the first process that was picked up for execution may go into IO. In that case, the second process will be given the CPU time, and then it will execute. In any case, the turnaround time for the individual processes will be high. So we will see what turnaround time, waiting time means in some time later. So yeah, the relation between turnaround time and things like that we will see a bit later. Anyway, so CPU utilization, that will also be low, of course, because we are just having one process that is being executed compared to two processes that are being executed. So that will also be low. That is a disadvantage. Okay, but the waiting time will also be low, because if you have just one process, so obviously the waiting time, it will not have to wait for its time for the CPU. It can directly get the CPU and it can start executing. Compare that to a situation where you have two or three processes. So there it may well be the fact that your process is not picked up first, so it may have to wait, and if it is preempted, then also it might have to wait. Okay, so things like that will occur. So coming to the third option, obviously we saw that the turnaround time will be low. Okay, and yeah, so that is the correct option. Anyway, let's get to the next question. So these are the scheduling algorithms. This question is related to the scheduling algorithms. So the scheduling algorithms are for the short term scheduler, as you may know. So which scheduling algorithm allows a process to run for a defined time quantum? Is it the shortest job scheduling algorithm, round robin scheduling algorithm, priority scheduling algorithm, or none of the above? So you might have studied about one more scheduling algorithm, that is the first come first serve scheduling algorithm. So we will have questions related to that next, but anyway, let's get back to this question. I am getting answers related to round robin scheduling algorithm. Anyone else would like to contribute? So what this question means is that the short term scheduler will pick up a process, it will let the process run for a defined amount of time quantum. After that, it will preempt the process and it will let some other process run for a defined amount of time quantum. So that defined amount of fixed amount of time quantum is generally decided by the operating system itself. So in which of the scheduling algorithms does this happen? So the scheduling algorithms, as you may know, they have to be pretty simple, since they pick up a job from the ready queue, and everything happens in the ready queue. So so these are the processes that need to be executed immediately, that are ready to be executed. So if the if the scheduling algorithm is itself complex, then it will take a lot of time to schedule the next process, which will waste a lot of CPU time, right? The long term scheduler, on the other hand, it can be a complex algorithm, because as the name suggests, it is called after long times. So it needs to schedule a lot of processes at a time for a longer amount of time, that can that will keep the CPU busy for a longer amount of time. So short term scheduling algorithms, they keep the CPU busy for a shorter amount of time. So that these scheduling algorithms have to be pretty simple. Anyway, the answer is round robin scheduling algorithm. So what happens in the round robin scheduling algorithm is it picks up a process, the scheduling algorithm, it picks up a process from the ready queue, it lets it execute for a certain defined time quantum as said here, and then we go to the, it is preempted. So this is the flow chart. So it picks up a process from the ready queue, so it gives it some burst time, CPU burst time. So that is executed for some for the given time quantum, and if the process is executed completely, then it then it goes to termination. And if it is not executed completely, then after the time quantum ends, it is resent back to the ready queue, and some other process is given the CPU time, right? So this is the flow chart for round robin scheduling algorithm. Let's move on to the next question. So the interval from submission of the process to the time of its completion. So what is that called? Waiting time, response time, turnaround time, or throughput? So which is correct? Would anybody like to contribute? From submission of the process to the time of its completion, what is that called? So we will see the relation between the times now, but anyway, let's first solve the answer. I'm waiting for answers. Anyone would like to contribute? Throughput, okay. So the interval refers to the time, okay. So time from submission of the process to the time of its completion. So what is it called? C, okay. Anyone else would like to contribute? So just check it. So anyway, let's go to the answer. Yes, turnaround time is the correct option. So yeah, this is the relation between the times that are related to CPU. So a process, once it is scheduled, it is in the ready queue. Once it is picked up by the long-term scheduler, it is in the ready queue. So that represents its arrival time. Okay. Then once it is picked up by the short-term scheduler, it gets the CPU time where it is in the running state. So the time from it being ready queue to it running, so that is referred to the waiting time. So although it is shown as a single span here, but once we get to this figure, we will realize that there may be multiple spans here actually. It may be that from the running state it can again go to the ready state, and there may be it may be waiting for the transitioning into running state again. Okay. Anyway, so the time that it is running, it is staying in the running state and actually then transitioning into the complete state, that is referred to as the burst time. Okay. where it has where this and once it has gone into this completion or the termination state, that time is marked as the completion time. Okay. So the turnaround time refers to the waiting time, that is this time plus the burst time. So this whole summation of the time is referred to as the turnaround time, from the time that it is arrived to the completion time. So that is referred to by this formula, that is the completion time minus the arrival time, that marks the turnaround time. And there are other formulas that we can associate with these 5 times. Okay. So as I was saying, that from a job queue, once it goes onto the ready queue, it is ready for execution in the CPU. Okay. So once it gets the CPU, it is in the running state here. Then it may be preempted, as we saw in the round robin scheduler. A process may be preempted back into the ready queue once its time has is over, or it may go into IO. In that case also, ultimately it will land up in the ready queue. So this time that it lands, sorry. I think somebody's microphone is on. Okay. Anyway, this time that it spends in the ready queue actually is known as the waiting time. So after and there may be multiple times that it will spend into the ready queue, and the time that it spends with the CPU, that is known as the burst time. So after it has completed execution, that marks the completion time of the process. Okay. Anyway, let's move on to the next question. So this is the first in first out algorithm. Sorry, I may have said first come first serve. So the algorithm is first in first out. So which among the following is the best describes the FIFO algorithm? So the first executes the job that came last in the queue, or does it first execute the job that came first in the queue? Does it first execute the job that requires minimal CPU time, or does it first execute the job that requires maximal CPU time? So which among the following do you think best describes the FIFO algorithm? Anyone would like to contribute? There is the first in first out algorithm. We have been talking a lot about queues. If you know about data structures, you may know that a queue is a data structure, yes, where a process comes in from one end of the queue and goes out from the other end of the you may think of it as a pipe. Like a process comes in from one end of the pipe and it goes out from the other end of the pipe. Okay. So that is what happens in a simple queue. There are other variations also. Anyway, I digress. So what happens in the ready queue? So anyone else would like to contribute? I have one answer. Okay. Anyone else would like to contribute? 2 answers. Anyway, let's get to the answer then. Yes, so yes, option B is correct. So yes, in the first in first out algorithm, what happens is that a job comes in from like the job that was first in the queue, that gets the first CPU time, and after that comes in all the jobs that are that came in next. So that is what happens in the first in first out algorithm. So that is what it means, right? So like think of the ready queue as a queue. So the first job that came in, first process that came into the queue, that is the first process that gets scheduled first. That gets scheduled, right? So that is what happens in the FIFO algorithm. Very simple. So yeah. So this is another question related to Amdahl's law, as you may have guessed. So anyway, so if a program has 70% serial code, okay, 70% serial code with 5 processors instead of, sorry, I missed the 1. So it will be with 5 processors instead of 1. So what will be the overall speed up? So if a program has 70% serial code, 70% of the code can execute serially only. It cannot execute in parallel. And now it has 5 processors instead of 1. It will be 1 here, not line. So it will be 5 processors instead of 1. So what will be the overall speed up of the system then? So before there was just 1 processor, now we have 5 processors that can cause 5x speed up, okay, that can cause at a maximum of 5x speed up. So what will be the overall speed up then? But the 70% of the code is serial, but the rest of the 30% is parallel. You can assume that safely. That can take advantage of the 5 processors that is now present in the system instead of 1 processor. So that can take advantage of the 5x speed up. So the 30% of the code will now execute at 5x. So then what is the overall speed up? What is the overall S that is achieved? Anyone would like to contribute? Anyway, let's get to the answer then. So yeah, the fractional speed up, that is 5, okay, and the fraction that was speed up that can speed up to 5 is 0.3, as I said, right? So if you put this directly in the formula, you will get the answer, right? So as I said, 70% is serial code. So in 0.7% of the code there is no speed up, but the rest of the 0.3 fraction of the code, sorry, 0.7 fraction of the code, not percent of the code. So in rest of the 0.3 fraction of the code, there is a speed up of 5. So if you put this directly in the formula, you will get the answer as 1.32. Okay. Anyway, let's move on to the next question then. So here you have first come first served. So assume that the following processes are scheduling using are scheduled using, again you have written first come first, sorry, it will be FIFO, and everything has arrived at time 0. Assume that everything has arrived at time 0 in the order P1 first, then P2, then P3, then P4, and then P5. So can you determine the average waiting time? So the waiting time refers to the time that it spends in the ready queue. So this is a non-preemptive scheduling algorithm. So it will not preempt any process in between once it is given the CPU. Assume that now you have to calculate the average waiting time, and assume that all of the processes have arrived at time 0. So these are the burst times that are given. Okay. So what is the average waiting time? Like you have to calculate the waiting time for P1, P2, P3, P4 and P5, and then divided by 5, since there are 5 processes. I will give some time for this numerical. Zero. Okay. So you have to calculate average waiting time, that is not just for a single process, You have to calculate the waiting time for all the processes and then divide it by 5. So what will be that? Anyone else would like to contribute? Okay, anyway, let's get to the answer. So these are the waiting times for the individual processes. So since P1 has come first in the queue, it will get immediately scheduled. So the waiting time for P1 is 0. As you may know that it will execute for 5 times, 5 seconds or anything. Anyway, for 5 CPU times it will execute. So the process P2 has to wait for 5 times then. So and then the process P2 will execute for 15 seconds. So the process P3 has to wait for 5 plus 15 times then. So 5 plus 15, the process P3 is waiting. Okay, so that sums up to 20, right? So the process P3 then gets the CPU and it will execute for 20 times, right? So the process P4 has to then wait for 5 plus 15 plus 20, that sums up to 40. Okay, so the process P4 has to wait for 40 times then. Now the process P5, it will get the CPU after more 40 times, right? 40 clock ticks. Okay, so the waiting time for P5 then comes out to be 5 plus 15 plus 20 plus 40. Okay, so if you so this sums up to I think 80. Yes, this sums up to 80. So if you sum all this, it comes up to I think 145. Okay, so if you sum all these things, all these 5, so divided by 5, so that will give you the average waiting time, which is 29. Okay. Yeah, that was it. Thank you for your time. These were all the questions. So today we have solved few questions related to Amdahl's law. There were few questions. Yeah, you are welcome. So there were a few questions related to scheduling also. So in the next class maybe we'll do a few more questions about related to scheduling. So the scheduling part was a bit less. We had solved more questions related to threads. So we'll solve more questions related to scheduling in the next class. Okay. Yeah. Bye bye. So hope to see you in next Tuesday's class. Thank you. You may leave now. Thank you all so much for joining. Thank you. So I'll be closing the session now. Okay.